In this lesson of 4.5, rational functions, we're going to focus on horizontal asymptotes. So horizontal asymptotes describe the end behavior of rational functions, whereas vertical asymptotes were somewhere in the middle behavior around the zeros. Horizontal asymptotes describe what happens where x approaches infinity. So if we're looking at a graph, we're looking over here where x approaches infinity, or where x approaches negative infinity if it goes in this direction. So we're looking at the end behavior with horizontal asymptotes. And that makes a lot of sense because when we talk about horizontal asymptotes, we're thinking of functions where if you divide them, which is what a rational function is, it's division. Let's think if we have f of x equals x to the 4th power plus 7x squared plus 3x divided by, let's do 3 different variations. Let's divide it by x plus 1 first. Now in theory, if we divide x to the 4th plus 7x squared plus 3x by x plus 1, and we did that with long division, our end result would be the degree 3. So theoretically, division here would result in a 3rd degree polynomial with some remainder probably. Let's graph this on a calculator and see what it looks like. So what I'm suggesting is that since this is x to the 4th and this is x, if we divided the highest degrees, it would look like x cubed of some sort. It would have this sort of end behavior where at the right it went up and at the left it went down. So let's take a look at that on a graph. Okay, so I've got this in my calculator. Before I do, let's look at what we learned in the last lesson, which is where's our vertical asymptote? It's going to be where this equals 0, and there is not a factor that cancels here. So at x equals -1, there will be a vertical asymptote. So look for that in the graph. So here we go. I'm going to graph it. I've already set the window to be a good window. Let me refresh it just a little bit so that it will graph the whole thing so you can see it happen. All right, there's the asymptote at x equals -1. It's going to negative infinity on the left side. On the right side, it's going to positive infinity. But look at the end behavior. As x goes to positive infinity, the y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. The same thing we would write for a 3rd degree polynomial, but now we have this added asymptote in here. So division with rational expressions gives us end behavior that's what we would expect, but it has some additional things. So as you would expect, if I had another one, g of x, if it was x squared plus 2x plus 5 over x minus 2, you would expect that our vertical asymptote would be x equals +2 from last night's stuff, and that if we divide x into x squared, we should have end behavior like x to the 1st degree. It should be some sort of line, our end behavior. So very similar to the one above. In other words, as x goes to infinity, y is going to infinity, negative infinity, negative infinity. Let's see if we can see that line when we graph this one. So my equation's in my calculator. Let's graph it and see. What I'm thinking is that there should be a vertical asymptote at +2, and I need to see some line that represents the end behavior in the middle. There's the asymptote at +2. There's the top of the asymptote. And here's what I'm saying is that my end behavior represented by some line in the middle. See how this is kind of straight, that's kind of straight. This is the vertical line at x equals 2 right here. So end behavior for rational functions is just what you would expect from the definitions we've already learned and feel very comfortable with. So how does that help us for today? So today we're going to focus on both horizontal and oblique or slant asymptotes. So we're going to define horizontal asymptotes as y equals a value c, whereas x approaches infinity, y approaches c. Some horizontal, so horizontal will be straight horizontal. We didn't actually see that in our examples yet, but we will. Whereas x goes to infinity, y approaches c, and as x approaches negative infinity, y also approaches c. In most cases. In some cases it will approach a different number, but in most cases they approach the same number. So horizontal asymptotes, they're horizontal lines. That means their y equals a number. It has to be a line. It has to be y equals to be horizontal. And these occur where p of x over q of x have the same degree. In other words, if you have an example like, this is actually number 3, if I had numbered any of them, if I said that f of x equals x to the third plus 2x plus 1 over x to the third minus x plus 1, what does that mean? It means that the degree of the top polynomial function and the degree of the bottom polynomial function are the same. That means they're growing at the same rate. And this may not make sense to you yet, but it will as we go through them. They're growing at the same rate. So if I put in x equals 10, I'm going to have 10 cubed here. And on the bottom, I'll have 10 cubed here. These numbers will be essentially the same. The smaller numbers will be incrementally smaller, so they're not always the same. This isn't an equation that equals 1, but because they're growing at the same rate, as x gets really large, the x cubed over the x cubed define what the function looks like. So I'm going to say, therefore, that's what the 3 dots means. They're growing at the same rate. Therefore, as x goes to infinity or even to negative infinity, x goes to positive or negative infinity, x cubed over x cubed define the end behavior. And we're going to look at this example on the calculator so you can have an idea of what I mean there. Okay, so here's my made up function. I have it in the calculator. And what I'm interested in here is end behavior. So horizontal asymptotes determine what's going to happen as x gets really large, like 1,000,000 or 1,000,000,000. I'm also going to have a vertical asymptote. I didn't make up an equation that has one that's easy to solve, but you'll be able to see it in the graph. And then I'm going to blow it up so we can look at end behavior. So here's the graph. It has some vertical asymptote here where if I set x cubed minus x plus 1 equal to 0, that would be some x value here. Has some other crazy stuff happening because it's third degree divided by third degree. But look what happens as we go to infinity. As we go to infinity, the top function is growing at the same rate as the bottom function. So they essentially cancel each other out. These numbers are going to be very small as we approach, say, 1,000,000,000. This is going to be 1,000,000,000 cubed, and this is just 2 times 1,000,000,000. This is huge, and this is inconsequential. And so essentially, we're looking at these growing at the same rate. And what happens is, in theory, this is like 1 over 1. The x cubes cancel, and this is y equals 1. is our horizontal asymptote. And let's see if we can see that. So I want to do two things. I want to look at my window and I want to make my my x values really big. I'm looking at x going to infinity. So let's put in 100,000 and then positive infinity, 100,000. There we go. So first I'm going to graph this and let's see what it looks like. It looks like a straight line all the way through. I can't even see the middle behavior that we saw on the other graph a minute ago. I can't see it at all. And if I write the equation, another one, y equals 1, which is what I'm suggesting is my horizontal asymptote, it's going to be the same line. It is not really that in the middle. It's just that this is so little, I can't see any more than that. Let's go back to zoom 6 so you can see the middle behavior happen and the line. Also note that this graph is going to cross the horizontal asymptote. So the red line coming through is a horizontal asymptote. This blue function is coming closer and closer to trying to be 1 for the y value. So as x gets to 10, this is trying to be 1. From the bottom, this one crossed the horizontal asymptote, but now this blue line from the top is trying to become 1 for y. So as x goes to 100,000, it's going to be really, really close to 1. It will never reach 1, but it will get very, very close to 1. These other values are the values that make it not 1 exactly, but it's getting really, really close to 1. So let's look again at some other examples and work out the math. We'll talk more about the numbers getting really big so you have an idea of what's happening. So horizontal asymptotes, let's summarize what we know so far. Horizontal asymptotes are always going to be y equals some number. Okay, horizontal asymptotes, y equals some number, and this number is some constant like 4 or 1 or 0. We only have horizontal asymptotes when the degree of the numerator, p of x, equals the degree of q of x. So when they have the same degree on the top and the bottom, that's when you have horizontal asymptotes. And there's one exception to that, and that is when p of x, how do I write this? P of x's degree is less than q of x's degree. And we'll look at that as well. So horizontal asymptotes, two situations, one, when the degrees are the same, or two, when the degree on top is smaller than the degree on the bottom. And in this case, the asymptote is always y equals 0 because this ends up being small over big, like we talked about yesterday. So let's look at these two examples with some actual functions. So let's say we have, we're going to call this example 4. So example 4, let's say that we have f of x equals 4x to the third plus 2x squared plus 1 over x to the third minus x. So we're just looking for horizontal asymptotes right now. We're not going to talk about the vertical. We will put those two together, but let's just focus on the horizontal. So horizontal compares the degree on the top and the bottom. Compare the degree top to bottom. In this case, they're the same. So if they're the same, we're going to take the ratio, we're going to look just at those terms that have the same degree, and we're going to look at the ratio of the leading coefficients. Ratio of the leading coefficients. Now, why is that? Again, we're looking at x values to infinity or negative infinity. So we're looking at humongous x values. And when you cube it, it grows way faster than this one or this one. So we only care about this. Now, if they grow at the same rate, because this is x cubed and this is x cubed, this is the same rate, because they have the same degree, we can essentially cancel these out and say at the end, at infinity, which is not really the end, but as it gets really, really large or really, really small, these cancel out and we're left with the coefficients. Our asymptote is going to be y equals 4 in this case. It's the ratio of the leading coefficients. And we can look at that graph and see that it will be 4. And let's do that just to have a visual. So hopefully you can see I've got my rational function there. I'm suggesting that y equals 4, so I can just put 4. So y2 equals 4 is the asymptote. And let's see what happens. I don't know how much I can see in standard zoom, but let's look and see. Okay, so there's 4. Got a lot of things happening in this graph, but then it starts to flatten out again. So what I care about is the ends. I do not care about middle behavior. That's going to be vertical asymptotes and zeros. But horizontal asymptotes are all about what happens at the ends. And you can see that the blue line is trying very hard to be the red line, and this blue line is trying to be the red line on this side. Notice how the blue line dips below the red line and then comes back up. It is okay to cross horizontal asymptotes because they're not domain breakers. Vertical asymptotes are. So hopefully you're getting a good idea of what it means to be a horizontal asymptote. It indicates the growth of the function and how fast it grows. These are growing at the same rate as we go to infinity or negative infinity, so we can compare the ratio of how they grow. This one grows 4 times faster on the top, so 4 wins out as far as the asymptote there. Let's see what happens if we have our second choice here. So when the degree on the top is smaller than the degree on the bottom. So what we're talking about in this example, so example 5, is that if g of x is going to be x to the 4th power plus 6x squared over x to anything bigger, so x to the 5th plus 1. I'm just making stuff up. So what happens is that we said before, if you had a small number over a large number, and we did this in the other video where we said 5 over like a million, but if we did 5 over 1,000 and recalculated that just so we felt good about it, 5 divided by 1,000 is 0.005. It's a very small number. So small numbers divided by large numbers are small, and they approach 0 as you grow your large number. So small over infinity, that's this example. So pause for a second, think about what that means. We're still talking about horizontal asymptotes, so we're talking about going to infinity. So as x goes to infinity, we're thinking about x to the 4th being something big, like a million to the 4th power. But a million to the 4th power is not as large. In fact, it's smaller than a million to the 5th power, which is a larger number. And as your numbers grow bigger and bigger, this ratio becomes, and again, these are unimportant because they are nowhere near x to the 4th even as we get to a billion, and x to the 5th is even bigger than x to the 4th. We're in this situation where when we divide a small number by a large number, and this number gets larger and larger and larger, we're approaching 0. So as a large number goes to infinity, we're approaching 0. So what I'm suggesting in this case is we do this same test. We compare the degree of the top to the bottom. In this case, they're not the same. So we compare them. In 2, we have a small one on the top, and we have a larger one on the bottom, which right away, that means that y equals 0. It means that this is going to infinity, and the unit is going to 0. Y equals 0 is the horizontal asymptote. It's all about the growth of the function. I got a little dicey there. As x goes to positive infinity and x goes to negative infinity, and which grows the fastest. So this one, if we graph it, which I'll do, you can see that the asymptote is not 1/1 or the ratio. In fact, this is 0. So here's my equation. I've got the function and y equals 0 just to see it. My function clearly looks like it's near 0 here. It's finding a vertical asymptote and another vertical asymptote. And then now it's going towards 0 again. So rational functions are way more interesting to look at visually. And we are focusing on the horizontal asymptotes today, looking at the degree of the top and the bottom. So in summary, with horizontal asymptotes, we're going to compare the degrees from top to bottom. If they're the same, then you have a horizontal asymptote. It's going to be y equals some number. It's going to be y equals the leading coefficient of the top over the leading coefficient of the bottom. And 2, if the degree is larger on the bottom, so degree larger in the denominator, there's only one choice. It's y equals 0 because it's small over big and it's going to go to 0. So horizontal asymptotes have these 2 characteristics. Now there's one more, and this is how I started the lesson with what we're going to talk about today. I talked about end behavior that's a little bit interesting. So we have one more that we're actually going to figure out today, and that's called an oblique or a slant asymptote. You'll see them written both ways. And this is a linear asymptote that's not horizontal. So it's going to be in the form y equals mx plus b. Okay? So it means that we have some end behavior that maybe goes to infinity on one side and negative on the other, or vice versa. So oblique or slant asymptotes have the characteristic that the degree of the numerator is 1 more, just 1, than the degree of the denominator. So you can see at this point how easy it is to get any of these asymptote rules confused. So let's look at an example here. So example 1 of this sort. I'm going to restart my numbering with 1. So example 1, if we said that f of x equals x cubed minus 8 divided by x squared plus 2. This is a situation where I actually do not have any vertical asymptotes. There's no way that this denominator equals 0. It doesn't always happen that you have a vertical asymptote. So looking at this is a positive number and this is a positive number. This will never equal 0. So I don't have any vertical asymptotes. What other asymptotes do I have? Now you compare the degrees of the highest terms that you have in each polynomial. X cubed is 1 more than x squared. That means if I divided x squared into x cubed, I'd have x to the first degree. That's a line. So that's a slant asymptote. So let's actually do that. So you're going to figure out that this is a slant asymptote. That's a shorter word to write, so I usually call it a slant asymptote because x cubed divided by x squared equals x. Okay, this is what I'm thinking. But what is it actually equal to? Let's actually divide this out with long division and find out the exact equation of our slant asymptote. So we're going to use long division here. We're going to say x squared plus 2 into x cubed plus 0x squared plus 0x minus 8. So let's do this division. X squared goes into x cubed, x times x squared is x cubed, plus 2x here, minus, cancel. Now I've got x squared minus 2x minus 8. X squared goes into x squared one time. X squared plus 2x, change the signs. These cancel. I've got negative 4x minus 8. So I have a remainder here. I have minus 4x minus 8 over x squared plus 2. Now the really, really cool thing about this is that if you followed what we did it all before, then you know that as x gets really large, this has a larger degree on the bottom as a remainder. So as x gets large, as x goes to infinity, this goes to 0. From the rules, degree larger denominator, it goes to 0. This actually means nothing as my function gets really, really large or really, really small because it has a larger degree on the bottom. So what is my line? My line is this, y equals x plus 1. So let's graph this and see if this function follows this line with its end behavior. So my slant asymptote here is y equals x plus 1. So we'll put this in and see what it looks like. All right, so notice I put in my rational function with a 1 degree higher on the top. I put in my line y equals x plus 1, and I'm suggesting that as x gets really, really large, this will describe my end behavior at this line. So there's my function. It doesn't have a vertical asymptote, but the x cubed minus 8 made it change a little bit. And you can see this line follows my x plus 1 really closely. And as I get really, really close, it's going to be an even better estimate of my line. Okay, so here I've got another example, 4x to the 5th plus 2x squared divided by x to the 4th minus 1. This is going to have a vertical asymptote at x equals 1. That's the number that breaks the denominator. 1 minus 1 would be 0. I'm going to have a slant asymptote because the degree is 1 more than it is on the bottom. And to figure out what that is, I'm going to do division, x to the 4th minus 1 into 4x to the 5th plus 0x to the 4th plus 0x cubed plus 2x squared, and then I'll probably have a remainder after that. So let's see what happens. So if I try to divide out, I've got 4x to the first power, 4, that will be 4x to the 5th, minus 4x, so minus 4x over here. And then change the signs, this cancels. Now I have 0x to the 4th. Oh, that other one should have been 0. That was so silly. That should have been 0. Okay, so the other one was off by a little bit, and I apologize for that. X to the 4th goes into 0 0 times, so I'm done. And I've got a remainder, but that's going to go to 0. This is my slant, y equals 4x with a 0 y-intercept. So this is my slant. This is the vertical. Let's see what happens when we graph. Okay, so I've got my rational function there. I have my better slant asymptote. And I do have a vertical asymptote now at x equals 1, so I'll be able to see that and hope with the slant asymptote. Let's zoom 6 and see if we can see it in the middle here. Otherwise, we'll have to reset our window. So there's a lot going on there in the middle. But hopefully my line is just going to cut right through there. So this is the end behavior for the blue line. It matches the red. This blue line matches the red. This slant asymptote, y equals 4x, represents the end behavior, not what's going on in the middle. We'll figure that out separately, although we do have that vertical asymptote right here at +1. And then I guess we've got one at -1 as well. Yeah, that's silly me. So we have 2 vertical asymptotes. If we saw this equal to 0, we'd have plus or minus 1, of course. So let me add that to my list. Plus or minus 1 vertical asymptotes. Okay, so in your homework, you've got horizontal asymptotes. They come from the same degree, top and bottom, same degree, top and bottom, or a larger degree on the bottom. One higher degree is going to be a slant asymptote, which is a line, y equals mx plus b, and you're going to do long division to figure that out. You're going to toss out any remainder, because as x gets really large, this will go to 0. And so that's what the practice problems have with those. You can graph on your calculator and check your work and see it happen. It kind of makes it all become real and not so arbitrary when you actually see it all come together on a graph. All right, thanks.